Good morning, everybody. It's a great pleasure to be here. It's because it's very inspiring to see good 300 people. Sure, yeah, 300 young researchers here in this audience, and you would think, wow, 300 people, 300 bright researchers coming to Singapore, so it must really increase the scientific capacity of this island a lot. But in fact, I should probably say to the organizers, it still feels quite minuscule because there are so many the scientific landscape in Singapore is so diverse these days that even this event doesn't change it much. So what I would encourage you to do is to go and explore the science in Singapore. Try to find you a good collaborator here, because indeed the climate for science in Singapore is extremely good, and I'm sure that you will find very good topic to work on together with the local scientists. So for today, what I wanted to do is to briefly tell you what we've been doing over the past maybe decade and where the topic of the material science going to go in the future. And let me just spend some maybe a bit lengthy introduction on where it all started for me. Is the two-dimensional material, and namely graphene. So so I don't think it requires any introduction. It's very, very simple material, just one layer of carbon atoms, and yet it has a number of very unique properties. It's, of course, is the most conductive, most thermally conductive, strong, stretchable, impermeable material, and so on and so on and so on. And really the most unusual, interesting point is that all of those unique properties are combined within one very, very simple material. So I don't mean this as a proper physics lecture, but I also don't want to let you off without any equations. So just try to survive for the next couple of slides, and then if you survive, then we should be okay. So as I said, graphene has a very, very simple structure. So it's only carbon atoms arranged in a honeycomb lattice. And yet, even though it looks very simple, it's, of course, we all know that the honeycomb lattice is not one of the simple Bravais lattices. It has 2 atoms per unit cell. So here I mark them yellow, so green and red. Of course, we all know that carbon atoms are blue, but and then because we have two atoms per unit cell, we have to, when we do proper quantum mechanical description of this crystal, we should allow our electrons to sit simultaneously on both atoms, and that gives us symmetric, antisymmetric configurations for the wave functions, and that basically leads to a very special dispersion relation, which is the linear dispersion relation. It's the same dispersion relation as for photons, for example. I won't go much into details. Why is it important? I just try to show you in a very simple cartoon, just explain why these materials, and actually lots of materials beyond that. So the linear dispersion relation is quite important in other materials like topological insulators as well. Why is it important and so unusual in the condensed matter physics? Because generally, all the materials which we have around us, like all the conductive materials which we have around us, can be divided into 2 big groups. Those where electrons conduct electricity, those where holes conduct electricity. It's like negatively quasi-particles conduct electricity, or positively quasi-particles. Now, to make it even simpler, here is an analogy to a country with a single party system. like for example Russia or North Korea, then electrons would be represented by people, and those people are free to move within the country. Now, if you want to control their movement, what you do, you create a checkpoint at the border control, and then you can control the flow of people. So what you need to do is to connect two materials with different conductivity, and then you can control the flow of electrons. So that's called the p-n junctions, and in a nutshell, that's basically all you need to know about modern electronics. So if you remember those p-n junctions, so that's you can build pretty much any semiconductor device. Now, graphene is fundamentally different from that because we have both electrons and holes at the same time described by the same wave function, because the equation which we use now is the Dirac equation, is the relativistic equation. And the analogy of the country would be United States. I should apologize. This is still from the previous election before Trump, so it still cannot cope with the last one. And people now represent electrons, but now independently if the state is Republican or Democratic, so people can go through the border without any control. So that's and so they can commute very fast, and so as electrons in graphene, they can really fly very fast through this material without any impedance, and that's why we have very high mobility for electrons in this material. And then because we can really control the how we assemble different layers, we can create two layers, we can rotate those layers, and we can actually create even more exotic quasi-particles, but because I don't have an example of a country for those quasi-particles, I'm not going to talk about them today. Just to show you how unusual is the physics which we observe for those quasi-relativistic electrons. So here is an even simpler cartoon. Many of you know that in the classical physics, if you run with a car into a wall, you will obviously crash it. Now, in quantum mechanics, there is this phenomena called tunneling, which allows you to go through this wall with a tiny probability. So the probability is so small that I won't try it neither with Jaguar, not even with the Volkswagen. So there is no chance you go through on a car. But in the nanotechnology, we see it all the time. We can see electron tunneling through the barrier, and it's quite easy to observe, and actually it's one of the problems which our electronics is facing in the future, because the sizes of our transistors and of the gate dielectric become so thin that this tunneling current plays quite an important role. Still, the probability is quite small. Now, for electrons which obey linear dispersion relation, as in graphene, the probability to go through is 100%. So that's quite unusual, counterintuitive, and yet we see it in our experiments in graphene. So, and that's really, for a physicist, it's one of the beauty working with this material. And as I said, the figure of merit, which shows how fast electrons propagate through the crystal, is called mobility. And it determines how fast your transistor would be operating. Like for typical silicon CMOS transistors, this number would be maybe 1,000. For CMOS, for typical HAMT devices, for the high-frequency electronics, it would be maybe 50,000, 70,000. For graphene, it's a good million. So it really tells you that probably graphene can actually operate at very high frequencies. And we already use this property of graphene for certain high-frequency devices already. Now, the optical properties of graphene are quite interesting as well, because you can ask me what kind of optical properties can you get from a material which is only one atom thick. We have millions of atoms between me and you, so if we have one extra atom, would it play any role? Well, in fact, it would. You can actually see graphene with your naked eye, not very well, but still. It absorbs about 2.3% of light, and what is interesting for a physicist is, of course, that this 2.3% is given only by the combination of the fundamental constants. So I guess I can't see Klaus yet. No. Right. Sorry, Klaus. So if you need to know if you need to know alpha, so Klaus will tell you everything you need to know about metrology in the next few days. But if you need to know alpha, the fine structure constant, all you need to do is to just look through graphene and divide the contrast by pi, and you get the most fundamental constant of this universe. Or if you forgot pi, look through graphene and divide by alpha. Right? But of course, for a physicist, this 2.3% is a huge number, very easy to measure. But for any application engineers, 2.3% is quite small, and that people would kill to have a material like this, which is conductive and transparent at the same time. You can use it for many applications which require transparent conductive coating, like touch panels or LCD displays, solar cells, and so on and so on and so on. And that's already led to a number of applications. So here is an example of the liquid crystal display, which utilizes graphene. But of course, we have lots of other. We have already commercial devices based on this material, which tells us that it's not only physics, but also the applications with graphene are very exciting. But before going to all the promises of what graphene will do for us in the future, let me just summarize a few applications which have been done already and which are already around us. So one thing is that it's the important contribution of graphene that it created workplaces. So lots of my former PhD students opened their startup companies and got rich already, so that's already secured their future. And this slide was meant as a joke until a few years ago I received my regular issue of the Glamour magazine, in which on one of the pages you read 5 jobs our kids will be doing, and they're right next to virtual architect, avatar stylist, active makeup developer, there is graphene engineer. And of course, if said by Glamour, it should be true, right? It should be correct. It also provides entertainment. I'm sure that this sitcom doesn't need an advertisement, especially in this audience. And in one of the early episodes, Sheldon, the main character, the string theorist from Caltech, he was scratching his head why electrons in graphene behave as massless quasi-relativistic particles. And he really spent a full episode long trying to recover this conundrum. And of course, you all know this already. Why? And the reason why he was struggling is because some of the formulas on these whiteboards are wrong. They're actually for the bilayer graphene, not for monolayer graphene. And then also it gives shelter if you ever fancy to live in Tallahassee, Florida, next to the high magnetic field lab there. You can also live on the graphene layer. But in reality, so graphene actually, even though we feel as a scientist, we feel that it has very, very special properties. In fact, when it turns to applications, it's not so special after all. It actually follows exactly the footsteps of many other advanced materials before it, because it goes, so first applications of many advanced materials are in composites, starting with the sport goods, where you can pay premium for a bit of the improvement. A couple of years ago, we collaborated with McLaren and with Richard Miller to create world lightest, unfortunately, world most expensive watch as well. So you can spend 1 million Swiss on 32-gram watch. Definitely by far most expensive if you calculate per gram, but still it worked. Now, if you don't have 1 million Swiss, you can splash £250,000 on this graphene car, and it's a small manufacturer, proper roadworthy cars. And starting this year, all of their cars, they use graphene composites for their body. And so we collaborated with them to create those composites. But to our surprise, the reason why they use this is not, as we thought, it would reduce the weight or increase the strength. It's actually the speed of production. Because of the thermal conductivity of graphene, the settling of the composites would be much faster, and the speed of production for any manufacturer, is as important as anything else. So it really shows you the importance of the collaboration between science and industry, because sometimes the solutions which we feel completely negligible are really important for those people. And of course, starting last year, well, actually starting 2 years ago, Ford started to use lots of plastic parts made from graphene composites under the bonnet, and in February they are launching even more parts. So about 100 parts in every Ford car will be made out of graphene. So going from the traditional composite applications, we go to more towards electronic application. So a couple of years ago, Huawei started to use graphene because of its thermal conductivity for thermal dissipation and thermal spreading. Most of its top models use graphene. The only reason why they don't use graphene everywhere, because unfortunately we still cannot produce enough graphene these days. We still need to ramp up the production. And going into proper electronic application now, we're talking about Cvd Graphene, proper monolayer, single layer material. And here we use, so here is an example of this sort of application where people created extremely sensitive photodetectors based on graphene and quantum dots, and you can vary the sensitivity range in really wide range, because it's really given by the absorption of the quantum dots, which bring the electron onto graphene, and by integration you can really achieve pretty much any sensitivity you want. So it's a commercial product now from Emberion, which is the Nokia UK from a couple of years ago. So as I said, there are quite a few examples where graphene already being used and replace other materials in the applications. But really what I want to do is to encourage you to think outside of the box and really try to create completely new applications, because we have quite a unique material with lots of new unusual properties combined in this one crystal. So we really we need to create completely novel applications which were not possible before, but which are allowed by graphene. So here is just one example we made a couple of years ago. So it's the adaptive contact lenses. You take a contact lens, put a layer of graphene on it, put another one on top, fill in the gap with the liquid crystal, and by applying voltage, you can change the optical focus of this contact lens. So you can adapt to your requirements. And for this application, of course, you need conductive, transparent, and flexible material at the same time, and that's all graphene. And research into these sort of applications are already starting and actually quite strong. One thing is to think about graphene as the perfect membrane, which is impermeable to any atoms. Nothing can go through. At the same time, what we can do, we can adjusted in such a way that we can make it selective for certain species to go through, and we can filter those and so on. And so what we have is the adaptive membrane on the atomic scale, and that sort of membranes you can use for desalination. Proton membranes are really important for the power cells. So that's for the fuel cells. So that's what those are the applications which really hope that they will change the whole landscape of our technology in the future. So water filtration, ion separation, all possible with those membranes. These days, people work a lot on DNA sequencing by translocating DNA through nanopores in graphene or in other 2D materials. Direct delivery with the nanomaterials, biosensors, and so on and so on and so on. So as I said, we're still facing a little bit of a problem with the enough production of graphene, because a long time ago we started with the Scotch tape method to produce graphene. You simply take a high quality graphite, the material which you find in your lead pencils, and you just exfoliate and get a monolayer out of this. Luckily, these days, of course, it's not very scalable, and yet we still use this method in our labs because it's the quickest and the cheapest way to get very high quality graphene. At the same time, we get these days lots of other ways how to produce graphene, like for example, for those for the proton membranes or for the photodetectors, you would use graphene which is produced by chemical vapor deposition. It's when you run carbon-containing species across a hot surface of a metal which has some catalytic properties. Those species crack on the surface, release carbon, which organizes itself in the layer of graphene. And really, so here you don't actually need, so it's a very simple technique. People grow square kilometers these days of graphene, and actually you can use pretty much anything, any carbon-containing source to do it. Just to give you an example that you can really do a lot of things with this. So some time ago, we wanted to create iron-doped graphene to study conda in it. So that's the sample preparation. Who can guess what it is? It's a very, very simple sample preparation. You basically prick your finger, put your blood on copper, stick it into the oven, and you cook it. You get both source of iron and carbon, and you get your iron-doped graphene. So just for the sake of advertisement of my group, don't worry, no students are hurt. Those fingers are mine, so I never cut fingers from my students, right? So and then you can go for other ways how to produce graphene. You can do liquid phase exfoliation. That's the way which you would use to produce graphene for energy applications for the composites, and some epitaxial techniques as well. Now let me switch gears and talk a little bit about the story beyond graphene. What have we been doing over the past few years? And the story goes like, so of course we used our lead pencils to produce graphene for many years, but of course our students, they're all very active, very just bright eyes, bushy tails. They always want to do a little bit more. And I said, okay, Kostya, we get all those grants, those millions from the funding agency. Can we finally buy not only the lead pencils, can we buy some other pencils as well? And the answer is yes, we can. And now if you exfoliate other materials, other pencils, what you can get is other two-dimensional crystals, not only graphene. And what it turned out to be that there are quite a few of those two-dimensional crystals in the world. So you can get one-atom thick materials from many other from many other layered crystals, and you can come out with really a large variety of the two-dimensional crystals, which collectively cover a huge range of properties, from the most insulating to the most conductive, there are transparent, opaque, there are ferromagnets, there are superconductors, and so on and so on and so on. And that really gives us quite an interesting opportunity. But before going to that story, just let me tell you a little story, just as a midterm entertainment. So some time ago, I was working in Manchester, and I spent 3 years of my life building the National Graphene Institute there. So that's how it looks now. That's how it looked maybe about 6 years ago when we were doing archaeological survey for this institute. So even in Manchester, you have to do archaeological survey. There were Romans, so there are something else, and we were quite excited to uncover rows of terrace houses from the beginning of Industrial Revolution in Manchester, but also the remains of a fairly large building over here, which was identified as an Albert Clubhouse. And the Albert Clubhouse in 1780s was the club for German expats who lived in Manchester. And we probably won't remember much about that club, but this gentleman was a member of this club. Again, I don't expect anyone to recognize by the face. I can tell you it's Engels. And we were quite excited that Engels was writing the conditions of the working class right underneath of my office in the National Graphene Institute. So every single building on the Manchester University campus supposed to be named after a famous Mancunian, like physics is the Schuster building, math is an Alan Turing building. So the knee-jerk reaction was, of course, can we call the National Graphene Institute the Engels building? The problem was that we were heavily supervised by the government, and when I just explained this idea to George Osborne, he just tapped me on the shoulder and said, "Kostya, we give you money to do research, not to explore your communist past." Same as the Communist Manifesto wasn't written by Engels alone. It would be stupid to stick only with graphene there, so we actually study many other materials as well in this. And that really gives us a lot of opportunities. But again, let me just make a little bit of the diversion here. So materials are extremely important for our life. We even call the ages we live in by the name of the materials, like the Stone Age, the Bronze Age, the Iron Age. A good question would be, which age are we living right now? And probably for the first time in history, we have a choice how to call our time. We can call it, the digital age, the silicon age, the nuclear. But at the same time, it's really important to make a choice, or maybe actually we don't need to make a choice. Maybe we don't need to bet on a single material. Because let me give you an example of what happens when you bet on a single material and really develop this technology beyond its capabilities. So here is the periodic table of elements which were used in silicon integrated circuits prior to 1990. So very, very simple technology: silicon, boron, phosphorus for doping, aluminum for interconnects, hydrogen, oxygen for passivation. So very, very simple technology. Even I could probably do it. Now, after 1990, we added copper for interconnects. Because of copper, we needed a few other elements as the diffusion barrier as the work function matching materials, but still reasonably manageable technology. So these days, if you look at the number of elements which we use in our integrated circuits, we basically use half of the periodic table. It's basically because we took a very nice, efficient technology of silicon from 1950s, and then we just, rather than replacing it, we're just changing and adapting it and so on, which is, of course, economically viable, but a good question, is it really the most efficient way how to develop? Because if I show you that our body actually, we have less elements in our body than in the integrated circuits, well, you would agree that we as human beings, we are capable of many more complex tasks than our computers. Probably we need to think a little bit outside of the box. And those examples are actually not unique to electronics. We generally bet on only a few materials around in our life. Like electronics is silicon, construction engineering, we rely on the strength of steel, the aerospace engineering, it's all aluminum. And so really few materials gives us only few choices, and that limits our ability to create new devices. Because if you think, well, if an engineer wants to create a new device, he or she would need first to check in the textbooks what silicon can do for me, was the band gap, was the work function, was the band gap of silicon oxide, and then create a new device within those constraints. Ideally, you don't want to do this. You want really create materials specifically for your applications, and for that, you need to be able to mix and match different materials together, and we have those examples, they're called heterostructures or composite materials, but in fact, it's still, the examples are still very limited. Ideally, you would like to create a new material by atom or layer by layer engineering for any new application, and that you will be able to really just assign particular property and particular function to any material, to any layer you want, and we do this already in other areas. We do use custom engineering, where you just design something at home, send the CAD file to a manufacturer, they 3D print it, send it back to you. We do it with the chemicals as well. You can design your DNA, ATG, send it by email. Within a week, you receive this DNA back to you. So the question is, can we do it with generally with the materials altogether? Can we actually expand this capability of designing new materials which are specific for applications into other areas of technology? And 2D materials provide one of the possible platform for that, because imagine if I come to work and I come to my lab and I have those two-dimensional crystals in front of me on the desk. So I have graphene, some semiconductors, some insulators. What I can do now, I can combine them back into a three-dimensional stack, but now in a way Mother Nature intended it to be, and I can create a completely new material, completely new stack, and I can encode the functionality in every single layer there, and then I can really encode not only the properties but actually the functionalities as well. And we are using this technology a lot these days, and even the very simple heterostructures, just a few layers, would give you very interesting, unusual results. Because of the reconstruction, you can get very unusual properties from those, and we already created new devices like tunneling transistors, light-emitting diodes, photodetectors, solar cells, and so on. Just to give you one example of that, actually there are lots of those two-dimensional crystals, and you can actually use a huge variety of properties there. Here is an example of a bit unusual tunneling transistor. So tunneling transistor is where you rely on electrons not going through the channel as in normal FETs, but for electrons tunneling from one graphene layer to another through an insulator. And so graphene is quite important here because of the low density of state. But so this insulator, in principle, we can use many different layered materials as long as we can make very thin layer out of this, so tunneling layer, so electrons can go through, but at the same time, so it should be no defects and so on. So we used many other materials for that, so like some semiconductors, tungsten, the selenide works well, boron nitride. Here is an example just to show you how versatile is the technology. We used, as a kind of a joke, fermuculides. So why fermuculides? Because it's basically clay. And why those? Because it's very ubiquitous material. To get it, you basically go to a convenience store and buy a cat litter boxes filler. And then you just exfoliate this material and you stick it into your tunneling transistor, and then you get your tunneling behavior, transistor behavior. And it's not very good transistor, but at the same time, because of some of the piezoelectricity or the piezoelectric properties of the fermuculides, we get some bistability, so you can probably use it as a memory device. So as long as you use these fermuculides before it goes to the cat litter boxes rather than afterwards, so you should be fine with those transistors. Now, here's another example of one of probably our most complex heterostructures. So those are lasers or light-emitting diodes, and we just graphene plays on the secondary role here, but so it's mainly done by some insulators and the semiconductors. So we properly design the band structure of those devices, and then we can make it to emit light or make it to absorb light, or whatever you want. And because the range of those 2D crystals is really huge, so we can play with many of them, so as the range of the light emitting as well. And probably the most important one for technology would be molybdenum ditelluride, because it sits right at the silicon photonic gap, so we can use it as a light sources for silicon photonics, which is one of the most one of the biggest problems for the silicon photonics in the future. So we go beyond that, so we go beyond 2D. For example, we can create single photon emitters based on those materials. And single photon emitters, they are very important for the, as you heard from the previous speaker, for the quantum telecommunication. So we can controllably create those in our materials, make light emitting devices based on the single photon emitters, and they are extremely bright, actually much brighter than in indium selenide, for example. What is good that those devices already start to go into the applications. I would say silicon photonics is probably one of the first areas where we can expect its application, because you want to be able to modulate light extremely fast for your telecommunication purposes, and that's all graphene because of the high mobility in this material, and that's one of the work which is very actively being developed in Europe by Graphene Flagship in collaboration with Ericsson. So we already produced a number of the prototypes which work in the real test beds where graphene is used as a modulator in silicon photonics devices. And for the future, the next generation of the devices, they will use other 2D materials as well, where we have the for example, light emission from molybdenum ditelluride, which will be quite nicely coupled to silicon waveguide. So we would hope that we will solve this problem of the absence of the light sources for our telecommunication. So now, of course, it's still a long way before we see this material engineering really kicking to the big applications, because it's still we can do it in the lab with very high precision. How to grow it in the large scale is still a good question. But at the same time, we start to see efforts in bringing those heterostructures in maybe a little bit less elaborative form to life already. And that's being based on a very simple technology that a part of proper two-dimensional crystals based on graphene, you can actually make inks based on those materials. So we can get graphene ink, but we can get inks of other materials, semiconducting or insulating. And what you can do now, you can put your inks into your inkjet printer and start printing those heterostructures. You print a layer of one material, of another material, put contacts where required, put another electrode, and the number of techniques with which you can do it is really huge. You can use inkjet printing or screen printing, so you can use many other technologies, and it actually works quite well for various applications. So now I also wanted to tell you another story, which just it's less about science, it's more about how efficient or inefficient way of working with those 2D crystals. So we've been working with those heterostructures based on graphene and other 2D materials for several years, and we published a couple of very good papers. Okay, not very good papers, but then I came across this story about the roots of those two-dimensional inks back into the 1940s, and this story takes us back to the Second World War. I should apologize for the quality of the drawing. So I drew those pictures one day on the airplane, and I never changed them. But basically, the story goes like this. So it's Second World War. Germany bombs Britain, Britain bombs Germany. So it's the first use of the radar technology, and British airplanes suffer huge losses because they can easily get detected by the radars. So you can really they get caught very easily. So what do you do to avoid it? You need to blind the radar. So how do you blind the radar? You just throw bits and just metal bits and pieces from the airplane, and so they were throwing so-called the window material. It's basically aluminum stripes. At the same time, aluminum is of course you cannot carry anything else apart of aluminum. Anything else would be too heavy. Aluminum at the same time is extremely expensive to throw, so people were thinking, what can you do to replace aluminum? So what they decided, someone smart decided that they want to replace aluminum with printed graphite on paper. And here is an account by Hubert Idle, who was working at the Adult and Weber company. It still exists in US. And this company, it was just a dye paint mixer company. So he was summoned to the War Office and charged with the creation of graphene ink, and we're talking 1940s there, right? And so here is his account so he was summoned to War Office. Someone gave him a task: create graphene ink and put it on the paper. So within 24 hours of the first report, by working through the night, 15 samples of different dispersions have been made. And the 2 promising samples were selected for bulk trials, and within a few days, a cask reached the mill. So really, for me, it's really impressive. Then for anyone working in the printable electronics, they know that there is always a trade-off between printability, how much binder do you put, and the resistivity, so how much of the active material, like graphene, do you put there. And here is the first account about graphene. So thin flakes that overlap the best and overlapping the best, and they studied the different dispersion methods. And they even put a graph of the weight of the coating against the resistance of per square. Typically chemist, no units at all, so no way to reproduce it. But for me, it's really nice example of the efficient PhD work. Like within 2 weeks, the mills were in full production and hundreds of tons were produced. So we've been working with all our might of the chemistry laboratories for a couple of years to create printable inks. These guys, 24 hours, 2 days, 2 weeks, done. So that's printable graphene. So, and okay, anyway, after several years, we've been working with this material, and we now have printable electronics based on graphene. We can print many different elements, like this is the RFID antenna, probably one of the most popular devices based on graphene. What really makes me happy is that a part of the UHF also print HF antenna, which require a layer, an insulating layer, and we start to use boron nitride there as an insulating layer for those antenna. So really go beyond graphene now in the printable electronics. So now, of course, these are RFID antenna, which are fully production, so it's a commercial technology. It doesn't require much science anymore. The major application for RFIDs is, of course, the Internet of Things. So we want things to communicate between each other. We need to give them a way how to transmit information. RFID is the ideal way. It doesn't require battery. It's quite a long range, 10, 15 meters. And so everything is great, apart of the fact that you only transmit your identification number, your name, which is not very interesting. Ideally, what you want is to really transmit some information about the environment, so we need to put sensors on those printable RFID, and that's exactly where other 2D materials are coming into play. So now what we do, we're not only printing the antenna, we also print temperature sensors, or we print light sensors, humidity sensors, pH sensors, and so on, or we can actually even combine them into one single combined sensor. And I believe that this technology can be really the basis for the future proper Internet of Things applications. So I think I will stop somewhere here and just give you a few takeaway messages that, so with graphene we're still having lots of fun doing fundamental science with graphene, but it is already fully integrated into the modern technology, and every month we see new and new applications of this material. Other 2D materials are equally important and equally interesting, and I think, but they're also getting from the labs into applications, maybe not as fast as graphene, but we see the signs of that. But actually the most interesting possibility here would be how to combine those crystals to create adaptive materials, functional materials for the future applications, which are not possible with the existing fixed materials. And what I want to do is to really thank all my collaborators over the years with whom I've been doing this work, and maybe just advertise that in NUS material science we do this next step, or working on the designer materials, but even beyond on the live adaptive materials. So we really combine different topics, the nature-inspired, the biomaterials, life materials, and we combine them together to create adaptive materials which can think, which can make a decision, and that's the work which we are going to do in the future. And I just advertise the professorships in the NUS. If you want to join us ever, you are very, very welcome. Thank you so much for your attention. Thank you.